All right, good afternoon. Now we're going to get started in just about a minute. Let's see, I want to get myself adjusted. Setting. All right. So yesterday we talked about, before the quiz, we talked about synthetic division and long division. Any questions about those two topics? Shall we go over one example? Let me know if you want me to do one example with long division and synthetic division. If not, we can move on. Any suggestions? All right, looks like I'm not hearing anyone want me to do a example. So in that case, well, you're going to have some practice problems in the homework, I'm pretty sure. I am just going to move on to talk about the next section. So we're going to begin with finding the zeros of polynomial functions. So that will be the focus today. Eventually, we're going to talk about rational functions in the second half of the lecture. This is 3.6, finding zeros of polynomial functions. Now, those functions are not simple functions like the quadratic functions, which you can either use quadratic formula or factor. And the sum of the cubic functions you can factor as well. But so the examples we're going to go over today is you probably cannot factor them, but still you want to find the zeros and maybe try to factor the polynomial function as much as possible. There's a few tricks that we can use. But the first thing I want to talk about is called the remainder theorem. Which says if a polynomial function f of x is divided by, let's just say x minus k, then the remainder, and as you can tell that we already did long division and the synthetic division, one of the two approaches will work, right? So long division will be f of x divided, sorry, not square root, divided by x minus k. And then we're going to have a remainder after a few steps. So that's what the remainder is. And if we use synthetic division, we take the coefficients of f of x, and then we're going to put the number, not k, not negative k, we take the number opposite from this parentheses. So we're going to take just k here. And if we do everything correct, the last number here will be the remainder. Right, the remainder could be 0, could be any number. So if a polynomial function f of x is divided by x minus k, then there's another way to find the remainder, which don't require long division or synthetic division. So the remainder is simply f of k. So if we take k and put into f of x and calculate f of k, that number is actually the remainder, which is a lot faster than long division or synthetic division. We just plug in there and evaluate f of k. That's it. So this is something that will be very useful if we want to find the remainder really quickly. Now, why is this useful? This is useful because not just that we want to find the remainder, it's sometimes we want to know if a remainder equals 0, because for polynomial functions, the following are equivalent. So the following statements I'm going to write, they are all equivalent. So if one is true, the other ones are true. So the first one is for polynomial function. Well, I should add for polynomial function, suppose f of x is divided by x minus k. So the first one is x minus k is a factor of f of x. The second one is x equals k is a 0 of f of x. So those two are equivalent. So if x minus k is a factor of f of x, then x equals k must be 0, or root of f of x. And then the remainder, remember the remainder we can get by taking k put into the function, f of k must equal to 0. So that's if we take k put into the function, we get 0. That's a remainder equals 0, right? In that case, we know that x equals k must be a 0 of f of x because it makes the function equal 0 when x equals k. And x minus k must be a factor. So those three are equivalent. So if one is true, and the others are true. So that's how important it is to know that the remainder can be found by f of k. So those three are equivalent. So I'm going to go over one example quickly. So example, given f of x equals 6x to the fourth minus x cubed minus 15x squared plus 2x minus 7. And we want to find the remainder of this f of x divided by x minus 2. So here's my function. If I take that function divided by the polynomial expression, I divide it by x minus 2, and I want to know what the remainder is. So I could set up a long division or use synthetic division, whichever you prefer, right? But if you don't like either, what you can do is just use the remainder theorem, which says the remainder equals f of k And the k value, this k here, is going to be the number opposite from x minus 2. It's kind of like the synthetic division is whatever's opposite from here. So we're going to take positive 2, put it into the function, and try to evaluate that expression. So that's going to be 6 times 2 to the 4th minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. So that's a lot quicker to find the remainder than actually doing the long division and the synthetic division, at least for most of us, because if we have a calculator, we type everything into the calculator directly. Okay, and I don't have a calculator and I'm being a little bit lazy today, so I'm not going to do the work. And I believe if everything's done correctly, it should be 25, but double check. I just copy from the notes. All right, so that's a quick use of the remainder theorem. Any questions? Okay, so I already talked about the 3 statements that are equivalent for polynomial functions. There's actually a name for this. This is called the Factors Theorem. Basically, what the Factor Theorem says for a polynomial function, x minus k is a factor of f of x if and only if, so IFF. So this means if and only if x minus k is a 0. X equals k is a 0 of f of x. Now, if you are not familiar with if and only if, what that means is that if one statement is true, the other statement must also be true. So if we know x minus k is a factor, then we know x equals k is a 0. It also goes the other way. If x equals k is a 0, then x minus k must be a factor. And both of this is going to tell us that the remainder f of k must equal to 0. So I like to think about all 3 statements are equivalent, but if you want to put it into a theorem, that's called the Factor Theorem. Right. So here's the example. It's not very good use of this example for now, but soon you're going to see more complex examples. So given f of x equals x cubed minus 6x squared minus x plus 30. So the first thing we're going to do, we're going to show that x plus 2 is a factor of f of x, which means that f of x, we could write it as x plus 2 times some expression. We don't know that yet, but we just want to show that's true. That's no remainder. So if x plus 2 is a factor, which means x equals negative 2 is a 0. So if we want to evaluate f of negative 2, we should end up with a remainder equals 0. So this means, so we can use remainder theorem to find the remainder and to see if it's equal to 0. See if the remainder equals 0. If it is equal to 0, then x plus 2 is a factor. So what we're going to do quickly is we're going to find f of the number we're going to put into the parentheses is not positive 2. We want to show x plus 2 is a factor, so we're going to take the number opposite from the parentheses. Instead of positive 2, we're going to put negative 2 into the function. And that's going to be, if we take negative 2 put into f of x, so that's a negative 2 cubed, putting a parentheses, right? Minus 6 times -2 squared minus -2 plus 30. Now, I just want to share with you one trick I always do. You probably know it already, and you probably practice it all the time. Every time I take a negative number, put into a function, I always add parentheses around the value I'm plugging in, because it's going to save a lot of mistakes, especially with subtraction. So now we can calculate each. So -2 cubed is -8, and then -6 times -2 squared, that's -6 times 4, minus -2 become +2, and a plus 30. And from here, we can actually just calculate everything, right? Because we get -8 minus 24 plus 2 plus 30 plus 32, and it turns out that we get 0. That's a good thing, right? Because remember, it says we want to show x plus 2 is a factor. We want it to have a 0 as a remainder. If the remainder equals 0, that means x plus 2 is a factor, right? So we confirm that. The second part to this question is find all zeros of f of x. Well, we know that -2 is a 0 based on that x plus 2 is a factor. So x plus 2 is a factor. It means that x equals -2 is a 0. What about other ones? Well, in order to find the other zeros, we have to know what goes into this parentheses that I don't know yet, right? The remaining of the factors. So that means that we have to sort of taking f of x divided by x plus 2 to figure out whatever is remaining after we divide by x plus 2. We need to find the quotient. So here we cannot avoid using either synthetic division or long division. So we still need to perform, need to find f of x divided by x plus 2. So I'm going to use synthetic division because it's less writing. So the function I have is, so which is x cubed minus 6x squared minus x plus 30. So that's a 1, -6, -1, 30. And we're going to divide by x plus 2. So I'm going to put -2 here. And if you remember, the process is that we're going to bring down the first number, 1. And then I'm going to take -2 times the 1 and put it into the next column. So that's going to be -2 times 1, that's a -2. And then I'm going to add. When I add, I'm going to bring it directly below. So -6 plus -2 is -8. And now I'm going to take -8, -2, multiply them, put it into the next column. So 2, 8, 16, +16. And then I'm going to add again. So -1 plus 16, 15. And I need to multiply by -2 with 15. So -2 times 15, that's -30. -30 plus 30 give us 0. So that's a good. So the remainder equals 0, but we don't care about that. We want to know what is a quotient. In this process, we begin with x cubed, x squared, x constant term. And then we end up with the quotient should begin with x squared term, x and a constant. So the quotient is going to be 1x squared minus 8x plus +15. So that's a quotient. And the factorization for f of x is going to be x plus 2 times this quadratic expression that's equal to f of x. Okay, good. We know we end up with the quadratic quotient. Can we factor that further, right? That's, if we can factor it further, then make it easier to find the zeros of the x-intercepts. So now let's try to factor this quadratic expression. We don't need to use long division or anything. We know how to factor. So we need two numbers multiplied by give me 15. And when we add, we get -8. So those two integers should be probably, so we get x, so 3 times 5 is 15. 3 plus 5 is positive 8, but we need negative, so we're going to make both of them negative. And there we have the complete factorization. And if we want to find zeros, we're going to set this equal to 0 to find zeros. So we get x plus 2 equals 0, x minus 3 equals 0, x minus 5 equals 0. So we get x equals -2, x equals 3, x equals 5. Now, if we look at the factors we had, x plus 2 has an exponent 1, x minus 3 has an exponent 1, x minus 5 has an exponent 1. So every 0 here has a multiplicity of 1. So all have multiplicity of 1. Any questions about this example? All right, so the next thing is sort of similar to what we did. In this case, we already know a factor, x plus 2, right? But what if we given a polynomial function and we don't know anything about the factors, and we don't even know how to begin factoring? Like just none of the factoring tricks we learned in the past works. How do we find the zeros? How do we factor the function? Now, here's something called the rational zero theorem. You're probably seeing it in Algebra 2 class. So rational zero theorem, which says if a polynomial function f of x has integer coefficients then every rational, let me circle this later, every rational zero of f of x has the form of p over q, where p is a factor of a0 and q is a factor of an. Now, you probably wonder, what is this, right? If you don't remember. So recall that a polynomial function f of x has the form of f of x equals an x to the n plus a n minus 1 x to the n minus 1 and all the way to a1x plus a0, right? So that's the standard form of a polynomial function. This is an, this is a0. What this theorem says that if the function has any rational zeros, means that the 0 is a rational number, could be put in the form of a fraction, like one number divided by another number. So each of these rational zeros f of x has could be written in this p over q form, and a p is always going to be a factor of a0. So p is a factor of the constant term, and the q is a factor of the coefficient of the leading term. So basically what this says that if we know the factors of the constant term a0, the leading coefficient an, if we know all their factors, then we can try to come up with rational zeros that might be a 0 of f of x. if the rational number we come up may not be a zero, but sometimes they are. So that's sort of like the guess and check work behind this theorem when we try to find the zeros of f of x. So I'm going to use the example to show you how this works. It's pretty confusing if I don't. Wait a minute, I'm muted. Oh, wait a minute. I just noticed that I was muted. Was I muted the whole time? Oh, okay, good. So probably just happened just now. Okay. Cool. I just got a notification that you are muted. I was like, was that happening all the time? But anyway, so let's use this theorem to work with the example. So the example I have is, so draw a line here. I'm going to put the example on the left side, and I'm going to put the steps on the right side. So example is we're going to find, so we're going to find all zeros of f of x, which is 4x cubed minus 3x minus 1. Right? By just quick inspection, we cannot factor this using the techniques we know, right? So, but we still want to find zeros, which means we're going to set it equal to 0, and then we have to factor, and then we set each of them equal to 0. But we don't know how to factor yet. How do we find the zeros? So here's the steps. So steps are here. So step 1, we're going to find all factors, including negative, so plus minus, all factors. I should say all plus minus factors of A0. A0 is -1. So here I'm going to put the actual procedure with this example. So A0 equals -1, AN equals 4. So factors of A0. So what are the factors of A0? Well, A0 is -1, so that means the factors are 1, all -1. There are only 2 options we could pick, right, for factors of A0. And then the second step is we're going to find all plus minus factors of AN. So AN, so factors of AN. AN is 4. So what are the factors of 4? Well, if we just look at positive, we know that 1, 2, 4, those are the factors of 4. But it could be negative, right? So -1 times -4, that works. -2 times -2, that works. So the factors don't have to be all positive. It could be negative. So I'm going to use plus minus of each. So plus minus 1, plus minus 2, plus minus 4. And if I expand this, so that's going to be 1, -1, 2, -2, 4, -2. Sorry, 4, -4. So those are the factors of AN. And the step 3, find all possible P over Q. So remember that P are factors of A0. So those are the P values. And the Q are all the factors of AN. So those are the Q. So P, we want to find all possible rational number P over Q. So that's going to be, so P over Q, the possibilities could be 1 over 1, which is 1, 1 over -1, or -1 over, so 1 over 1, 1 over -1. We could also have -1 over 1. It doesn't change the value, it's still going to be -1. -1 over -1, right? That's still going to be +1. So I'm not going to write all 4. I'm just going to write 1, -1. You know what? I'll use a different line. 1 over 1, 1 over -1. We could also have 1 over 2, 1 over -2, 1 over 4, 1 over -4. And then we could also have -1/2, -1/2, -1/4, -1/4. So it looks like we got a lot of possibilities. But if we look at each of those values, really not that many, because we have 1/1 is 1, 1/-1 is -1. And then the next two are repeating, so I'm not even going to write those two. Then I have 1/2, 1/-2, that's a -1/2. Then I have 1/4, 1/-4, which is -1/4. But then the rest are repeating again, right? Because -1/2 is -1/2, I already have it. And those last four are repeating. So it looks like we might have a lot of options, but in reality, we only have 6 possible rational numbers that could possibly be the 0. Does this make sense? And then we're just going to test each one of them. We really don't have to test a lot. To be honest, the trick is to test one of them until we get a remainder equals 0. So step 4. So evaluate each P over each f of P over Q to see if f of P over Q equals 0. We want the remainder equals 0 in order to have a 0 or have a factor. So what we're going to do is we're going to take each of this P over Q, and then we're going to take it, plug into the function to see if we end up with f of P over Q equals 0. Okay. Now I'm just going to pick one and put in there. If I end up with the remainder equals 0, then I'm not going to try other ones. I'm going to use division to simplify to find the quotient. All right, let's see. Let's try P over Q equals -1. Let's try -1 first. So if I take -1, put it into the function, remember my function was 4x cubed minus 3x minus 1. So if I take -1, put in there for x, so I get 4 -1 cubed minus 3 -1 minus 1. And that's going to be 4 times -1, that's -4, minus 3 minus 1, that's plus 3. And then minus 1 looks like that's not going to give me a 0. So that's not equal to 0 because that's equal to -2. So that's not good. So -1 is not going to be a 0. Right. Obviously, when we have a problem like this, you want this to begin with 1 because 1 is always a good number to plug in. So let's, just for the sake of trying, so let's try, let's see, 1/2. Right, see if that's going to be a 0. So if I take 1/2, put into the function, so f of 1/2 is equal to 4 times 1/2 cubed minus 3 times 1/2 minus 1. So let's see what we have. So 4 times 1/2 cubed, so that's a 4/8 minus 3 times 1/2, so that's minus 3/2 minus 1. So if I come in denominator, so I get 4/8 minus 3 times 4, that's a 12/8 minus 8/8. Is that going to give me a 0? So it looks like that's 4 minus 12, -8, -8. So that's -16/8, -2. So again, the remainder is not 0. It's not equal to 0, which means 1/2 is not a 0, right? So sometimes you might have to try a few numbers, but I would say usually begin with a small number like 1, -1, 2, -2, and then go from there. Okay, now let's try 1. Try 1. So f of 1 is going to be 4 times 1 cubed minus 3 times 1 minus 1. So it looks like that's a 4 minus 3 minus 1, bingo. So that's going to be a 0. So the remainder equals 0, therefore 1, x equals 1 is a 0 of f of x. Right? Now you could keep going, like take we did 1, -1, 1/2. You can take -1/2, 1/4, -1/4. You're going to have to try all of those. if you want to go down the list. But I don't. Usually with the quadratic expression or cubic, with the cubic or quadratic or quintic, I just find 1, 0 and then try to find a quotient from there. So I already know x minus 1 is a 0. So x minus 1 is a factor. So I'm going to have f of x is equal to x minus 1 times some factor. So instead of keep trying all other rational numbers, I'm going to actually find out this quotient using synthetic division or long division. So let me use synthetic division to find quotient. So I begin with 4x cubed, so that's a 4. And I don't have x squared, so there's a 0x squared. Then I have negative 3x and a minus 1. So I already know x minus 1 is a factor. So I'm going to put 1 here. So we bring down the 4. And 1 times 4 is 4. 4 plus 0 is 4. And then 1 times 4 is 4 again. Negative 3 plus 4 is 1. 1 times 1 is 1. And then that gave me a 0 as a remainder, but I don't care. So the quotient is given by those 3 numbers. So that those 3 numbers can tell me the quotient is going to be, this is x cubed, so this must be x squared. So it's 4x squared plus 4x plus 1. Is a quadratic expression. Maybe we can factor this, right? To factor this quadratic expression, I'm going to write something different. I'm going to write this 4x squared as 2x squared plus 2 times 2x, that's the 4x, and the plus 1. Make it easy to factor. So that's going to be x minus 1. So I have 2x squared, so that means each parentheses is going to have 2x. And then I need 2 numbers that multiply, give me 1. When I add, give me 2. So don't worry about the 2x in each parentheses because that's already taken care of. So 2 numbers multiply, give me 1. So that's a 1, 1. And a 1 plus 1 is 2. Perfect, it works well. So it turns out that the actual factorization at the end is going to be x minus 1, 2x plus 1 squared. And if we want to find all the zeros, we set it equal to 0. From the first part, x minus 1 equals 0, we get x equals 1. We already got this earlier. So known this. But then the second part, 2x plus 1 squared equals 0. So that means we can take a square root and we still have 2x plus 1. That's going to be 0. So we can minus 1 on both sides, divide by 2. So we get x equals negative 1/2. Now note that, I know there might be a question. I'm almost done here. So note that because we had 2x plus 1 squared in the factorization, that square is going to tell me that x equals negative 1/2 has multiplicity of 2. Because of the square. So those are all the zeros. 1 has a multiplicity of 1, but negative 1/2 has multiplicity of 2. Okay, I'm going to stop there. I know there might be questions, so it's a very complicated process if you have never done it before. It's long, obviously, right? But the first step is finding the factors of the A0, the constant term, finding factors of AN, the leading coefficient, and then we're just going to take those factors and try to combine them in many ways as possible and try to find out possible rational numbers. And try each one of them until we get a remainder equals 0. So to find the remainder, you just take each of this value, put into the function until you get a 0. And if the remainder equals 0, in this case, when we have x equals 1, and then we're just going to take the x equals 1 as a 0, give us x minus 1 is a factor, then we can use that factor to perform the division to find out the quotient, which is going to be quadratic in this case, which we can always try to factor this quadratic expression if possible. And then from there, we can solve for the zeros. All right, I know that might be questions. So any questions on what I did, feel free to unmute yourself or put in the chat box.
So I actually have just a quick question. So A0 equals 1, that makes sense. So does AN always just kind of, are we always using 1 to get 4?
Right. So,
okay.
so here we're not talking about prime factorization, we just talk about any factors, right? So 1 times 4 is 4. So if you have AN equals 4, you're definitely going to have 1, 4, -1, -4 as factors.
Okay. All right. Thank you.
Yep. And also any other number between, right? Yeah. But if we have 1, like if, for example, if we have A0 is 1, the factors is going to be always 1 and a -1, right? Because if we take -1 times -1, we get 1. If we take 1 times 1, we still get 1. But if we have AN equals -1, again, it's just going to be 1 and a -1. What I have done in the past with this type of problem is that it doesn't matter what the sign of AN and A0 are. I always put plus minus signs in front of the factors, because even if the constant term or the leading coefficient is negative, when you try to find the factors for the negative number, you still have 1 positive, 1 negative, right? So it doesn't matter which one is which. Any other questions? Okay. All right. So I think it might be helpful to work with another example here. So again, I'm going to use another example. So the example I have is, find all zeros of f of x equals 3x cubed plus 9x squared plus x plus 3. So we're going to find all the zeros, but in the middle, we're probably going to factor f of x. So here, let me begin with, so the first step is finding the factors of A0. A0 is 3. So we need to find all factors. So P could equal to, it's 3, so it's going to be 1, -1, so plus minus 1, 3 plus minus 3. Because if we have 1 times 3, give us 3, but each of them could be negative, so plus minus. And let's see, AN is the leading coefficient. In this case, it's also 3. So the factor is going to be, again, 1 or 3, but it could be plus or minus for each. Okay, and the next thing is to find the all possible P over Q. So let's see, we have positive 1 for P. So that could be 1 over 1, 1 over -1, 1 over 3, 1 over -3. And then we could also have, let's see, -1 for P. So we get -1 for each one of them. So -1 over 1, -1 over -1. But it turns out that they're going to be repeating those 4 numbers. So I'm not even going to write it. And then we could take positive 3 for P. So you get 3 over 1, 3 over -1, 3 over 3, 3 over -3. And we could also take -3 divided by 1, -3 divided by -1, -3 divided by positive 3, -3 divided by -3. Again, at the end, it's just going to be repeating those 4 values. But if we look at those 8 numbers together, some of them are also repeating, right? Because the 3/3 is 1, and the 3/-3 is -1. So we don't even need to consider those two. So at the end, we just end up with 6 numbers. So that's a 1. I shouldn't use the equal sign. Oh, well, that's okay. 1, -1, 1/3, -1/3, 3, -3. Right, so all of those could be a rational zero of f of x. So what we have to do next, at least to find one of them that works, right? I don't know what you prefer. Like for me, I always take 1 and a -1 to begin with. So let's see, try 1. So if I take 1 put in there, so f of 1, that's going to be 3 times 1 cubed is 1 plus 9 times 1 squared, which is 1 plus 1 plus 3. Again, that's not going to be 0. I don't even care what it is. It's not a 0 by just quick inspection. It's going to be a positive number. And then try -1. And the f of -1, that's going to be, well, let's see. If we put -1 in there, so we get 3 times -1 cubed plus 9 times -1 squared plus -1 plus 3. And then if we do it quickly, and we know the first term is going to be -3. Next term is +9, that's 6, minus 1 plus 3. And I know that's not going to be 0, right? I know we can try 1/3. And it turns out that if we take 1/3 put in there, that's also not 0. And the -1/3 if we put in there, and it's also not 0. And we can try 3. And if we take 3 put in there, it's also not 0. And you probably think, okay, does it look like maybe none of the numbers works, which is possible, but it's actually not possible when we have well, it is possible because we might have like a irrational zeros in some case, but usually irrational zeros, they come in pairs, and the complex zeros, they also come in pairs. So if we have x cubed, we're going to have 3 zeros. One of them must be rational. So take -3 put in there, f of -3, which is going to be 3 times -3 cubed plus 9 times -3 squared plus -3 plus 3. Did I do it right? Looks like we did. All right. So now if we calculate everything, so 3, God, don't know what. Okay, -3 cubed is -27 times 3, so that's -81. And the plus 9 times 9, again, that's 81, so that goes away. And then plus -3 plus 3, so that goes away, so end up with a 0. So this example, clearly we just, if we try this method, the very last possible P over Q is actually the 0 of the function. Now, there's really no other quick way other than just try them, because sometimes 1/3 might work, and -1 might work, right? So we just have to keep trying. And obviously, to be honest, you don't even have to do a lot of this by hand in the future, because we can just write a simple computer program that does all the work. All right, so we found out that when we have x equals -3, we end up with a remainder that's a 0. So x equals -3 is a 0 of f of x, and that means x plus 3 is the factor. So that means f of x can be written as x plus 3 times some expression, and we're going to find that. So this expression is actually f of x divided by x plus 3. So this, let's call this the quotient. This quotient is equal to f of x divided by x plus 3 is equal to this factor right here. And we need to find it. At least to my understanding, synthetic division, probably a quickest way to find this quotient. So let me write down the synthetic division setup. So that's going to be, so we had a 3, 9, 1, 3. So that's a 3, double check, the 3x cubed plus 9 plus 1 plus 3. Okay, that's right. And then we're going to divide by -3 because x plus 3 is a factor. So I'm going to bring down the 3, and the 3 times -3, that's going to be -9. And a 9 plus 9 is going to be 0. And let's see what else. -3 times 0 is going to be a 0. And 1 plus 0 is a 1. -3 times 1 is -3. And the plus them give us a 0 as a remainder. That's good. But I only care about those first 3 numbers. So this is x cubed. This one must be x squared to begin with. So the quotient is going to be 3x squared plus 0x plus 1. If I put into the parentheses, so I get f of x is equal to x plus 3 times 3x squared plus 1. Can we factor this, the second parentheses? It turns out that no, we cannot factor the second factor here, but we can still solve for zeros, right? So we set this equal to 0. So we get x plus 3 equals 0, which is x equals -3. We already know this 0 from the trial and error. And then we have the second expression, 3x squared plus 1 is equal to 0. So move the 1 to the right side. So, and divide by 3, so we get x squared equals -1/3, right? If I move 1 to the right side, I get -1 divided by 3, -1/3. And I can take square root, so x equals plus minus square root of -1/3. Now, so here, I know we didn't talk about complex numbers, so we assume that you already know them. Every time we take a square root of a negative number, so the square root of -1, that's a complex number I. So this is going to be plus minus square root of 1/3i. You can write this as plus minus square root of, let me put it on the side, so square root of 1/3. That's going to be square root of 1 over square root of 3. That's going to be 1 over square root of 3, but we don't like to keep square roots in the denominator, so we're going to multiply by square root to the numerator and denominator, so we get square root of 3/3. So those are equivalent. So we end up with plus minus square root of 3/3i. We end up, this is not a real 0, this is the complex 0. And the two of them, one is positive √3/3i, the other one is negative √3/3i. Any questions? One comment about this complex zeros at the end. So when we solve a polynomial function of complex zeros, always come in pairs. As they say, complex always come in conjugate pairs. What that says is that if you have one complex 0 at the end, that means there might be another one come with it. There are always going to be 2 or 4 or 6 complex zeros. It's never going to be 1 or 3 or 5. So they always come in conjugate pairs in the form of a plus bi or a minus bi. A could be 0, b could be 0. But for complex zeros, usually the b is not 0. Any questions? All right, if you don't have any questions, let me go over another, a different example, slightly different. But if you have any questions, feel free to, like I said, use the chat box, unmute yourself. So the next example is, suppose we don't know the polynomial function, we have the roots already. Suppose let's see. Suppose we don't know the polynomial function. But we know the roots. And the roots are the real roots, well, the real zeros are 1 and a negative 1/2 with, let's see, I need to do this. With, so the 1 has a multiplicity of 2. Let me just rewrite this. With multiplicity of 2, and then what did I say? Negative 1/2 has multiplicity of 1. Oops. And there's also a complex 0 that's given, which is 2 plus I. And this function, we also know that f of 2 equals 6. So that's some information we know. So what we want to find is, so we want to find this polynomial function f of x. Okay, so this is what we know. We know that it has 2 real zeros, and we also know one complex 0 is given, and we also know that when x equals 2, we get 6. Right? We want to find this polynomial function. The way to find it is that we're just going to recognize that if we have a, for example, if we know that the real 0, x equals 1, has a multiplicity of 2, so that means that's going to be a factor. So from x equals 2 with multiplicity of, sorry, x equals 1 with multiplicity of 2, we know that x minus 1 squared must be a factor in the polynomial function. Is a factor. And then we, from x equals negative 1/2 with multiplicity of 1, then we know that x minus negative 1/2, or another way to say x plus 1/2, is a factor. Right? But you probably think, okay, can we do the same thing with complex zeros? Certainly we can do that. So from x equals 2 plus I, we know that x minus 2 plus I, so be careful here, you have to add the 2 plus I as a number, put it into a parentheses first. So x minus this complex number is a factor. Okay, well, is that all? No, it's not, because that's actually another one, another 0 that's, even though it's not written, but it's there. So this is sort of going back what I wrote earlier in with red. So it says complex zeros always come in conjugate pairs. So if you have one complex 0, that means there must be another one. So here we have a complex 0, x equals 2 plus I. So that means 2 minus I must also be a 0, even though it's not given, but it's there. it's a 0. So that's something to watch out for. So from x equals 2 minus I, we can also write down a factor for the polynomial function, which is x minus parentheses 2 minus I. So that's what we have. We have 4 factors here. Then we can write down the polynomial function f of x, which is equal to x minus 1 squared times x minus negative half, so x plus half, and then x minus 2 plus I. So I'm going to expand that and write it as x minus 2 minus I. And then the last one is x minus 2 minus I, so x minus 2 plus I, if we distribute the negative in the parentheses. Well, is this the answer? Well, not really, because we need to add a constant a in front of it. We still need to find out what a is. And that's why we need the last information given, f of 2 equals 6. So we're going to use that information to decide what a is. So at the end, what we're going to do is, so let's use f of 2 equals 6. So if I take 2, put in x, and the 6 for y, so I get 6 equals a, 2 minus 1 square, which is 1, not too bad. And then 2 plus 1 half, that's okay. And 2 minus I, and a 2 minus 2 plus I. So it turns out that with this example, it's not that crazy. So we get a, this is 1, times 2.5. So let me just say this is a 1. This is going to be 0 here, minus I, 0 plus I. We just drop the 0. So we get a times 1 times 2.5, that's a 5.5, times negative I times positive I, and that's equal to 6. And if you remember with complex numbers, if you have I times I, so I squared equals I times I, which is square root of -1 times square root of -1, which is just -1. So here we have negative I times I, so that's a negative of -1. So that's -1, but outside we still have a negative. So we get negative of -1, which is +1. So I get 6 equals negative I squared is equal to +1. So I get 6 equals a times 5/2, and the a equals, what is it? 6 times 2 over 5, 12 over 5. So the function at the end is f of x equals 12 over 5. Did I make any mistakes? X minus half. Okay, I think we're good. So 12 over 5, and then we have x minus 1 squared, x plus 1/2, x minus 2 minus I, and x minus 2 plus I. And generally, we actually simplify the last two to something nicer by multiply it out or FOIL, whichever could be used. But for the sake of this problem, I'm just going to leave it here because I don't see any hope of continuing to rewrite this. All right, any questions? Okay, let's see. All right, let me know if this makes any. So this is actually similar to what we did a while ago. If you remember, we had an example that given a polynomial function that probably looks like this. I don't know if that's the exact example, right? But it's something that looks like this. So it asks you to find a formula for this polynomial function. What we did is basically the same process, right? We've identified the x-intercepts and the multiplicity based on the shape. then so we did f of x equals a times some number squared times some number cubed. I mean some expression cubed. And then what we did is we use a y-intercept or maybe another point to find the a. So that's really the same process. So here we're not given a graph. We just tell you that, okay, so those are the zeros and then multiplicity. And this is a complex zero. So we just do the same thing. All right, on that note, let me know if you have any questions. I'll be around. Let's take a few minutes break. So let's be back. It's 7:13. So let's be back here at around 7:20. Is that a good time? All right, so let's take a break. Back by 7:20. All right, welcome back. So in the second half of the class, I want to talk about rational functions. So 3.7, rational functions. You probably all know what rational numbers are. So rational functions basically is a function can be written in the form of, so let's say f of x is rational function. It can be written in the form of p of x divided by q of x, where p of x and the q of x are polynomial functions. A example that you all know of is f of x equals 1 over x with a graph, looks like in the first and the third quadrant. And then a similar example would be f of x equals 1 over x squared, and the graph will be in the first and the second quadrant. Now, you probably already know a lot about rational functions, but I just want to quickly brainstorm. So rational functions usually have vertical asymptote and perhaps horizontal asymptote. So vertical, I'll write it down later, and horizontal asymptote, same thing with this one. But another thing I want to quickly remind you is that if we have a graph that looks like the first one, so near this vertical asymptote, the y-axis, the two graphs, one going up, one going down, they point in the opposite direction. We see the function diverges at this vertical asymptote. So function diverges at this vertical asymptote. It just means that they don't go to the same direction. They go to the opposite direction. And the second example, the 1 over x squared, near this vertical asymptote, the y-axis, both ends sort of going upwards together, right? So they converges. So f of n converges at this vertical asymptote. Now, it's not just random. The reason that they converges has to do with the power near this vertical asymptote. So the power is the power of the factor in the denominator. So in this case, in the first one, we have x to the first power. So there's a 1 here. It's an odd number. So that's why it diverges. And the power of the x in the denominator of the second function is 2. It's an even number. So that's why it converges. So if the exponent of the factor in the denominator is odd, it's always going to be divergent near this vertical asymptote. If the power of the factor in the denominator is even, the function always converges. It's just something I want to get it out of the way. So with rational functions, the first thing we can talk about is vertical asymptote. So vertical asymptote is a vertical line, a function that the graph of f of x approaches. So a notation would be, it's always the vertical asymptote is always happening at a specific value, like at 2 or 5 or -5. So we write the notation x goes to a, so as x goes to a, f of x is going to go to either infinity or -infinity, depends. Doesn't have to be both. It could be just positive infinity or -infinity. So that's where the vertical asymptote happens. One thing to note that f of x cannot cross a vertical asymptote, because let's just say this is my vertical asymptote. If a function, let's say the function goes like, should be going up like this, right? And if it crosses, that means at some point it must be crossing it. Well, if it crosses and then going up, that means it's not a function anymore because it's no longer past vertical line test, right? So it doesn't pass vertical line test anymore. So that's usually what happens with continuous with rational functions. So you cannot have the function crosses vertical asymptote. And then the next thing is horizontal asymptote. Is a horizontal line that the function approaches. That f of x approaches as x goes to positive or -infinity. So it's not, horizontal asymptote is not what the graph approaches for x equals 5 or 10. It's what the function approaches as x goes to infinity or -infinity. So the notation is as x goes to infinity, f of x perhaps goes to plus or minus infinity, but you could also have x goes to -infinity. The function goes to plus minus infinity. It could be one of them, but doesn't mean all of it. So that's horizontal asymptote, but note that horizontal asymptote is when x goes to infinity, but vertical asymptote is when x goes to a number. Oh, sorry, I made a mistake here. So horizontal asymptote is when x goes to infinity or -infinity, the function approaches a number. That's the k. It's not infinity, apologize for that. So that's a horizontal asymptote. And note, f of x can cross a horizontal asymptote. So what that looks like is, in the long run, the function might be approaching some number in the long run. But in the middle, the function perhaps could go above it or below it, and then eventually approach it, or something like this. It's perfectly fine for function to cross the horizontal asymptote. That's totally fine. It doesn't violate the definition of a function. Okay, let's see. So we talk about vertical asymptote, horizontal asymptote. Let's look at, so let's talk about how to find them. So here's the example. F of x equals x squared minus x minus 2 divided by x squared minus 4. So what we're going to do is we're going to use this example to find horizontal asymptotes, vertical asymptotes. So before I do anything, to find the horizontal asymptote, it's a little bit easier in my understanding, because it's just a behavior when x goes to infinity or negative infinity. So that depends on the leading terms. So to find horizontal asymptote, we're going to take leading terms of numerator, well, not take, consider only leading terms of numerator and a denominator. And ignore everything else. So if I only consider the leading terms of numerator and denominator, so I get f of x, the leading term of the numerator is x squared, the leading term of the denominator is x squared. So if I take x squared divided by x squared, simplify, I end up with 1. So this is y equals 1. This is my horizontal asymptote. What that says is that as x goes to infinity, the function is going to approach y equals 1. So y equals 1 is here. So as x goes to infinity, the function basically becomes flat, approaching y equals 1. Same thing on the left side. So that's the horizontal asymptote. Now to find the vertical asymptote, we don't take the leading terms. To find the vertical asymptote, what we have to do is we have to factor both numerator and denominator first before we find the vertical asymptote. So let me use a different color. So step 1, factor f of x completely. And step 2, simplify with notation, because there's something we need to pay attention to when we simplify. I'll explain what that means. And the step 3, we're going to set the denominator equals 0 after we simplify. All right. So let me use this example to show you what I mean by step 1 to 3 to find the vertical asymptote. The first step is factor. Now, the reason I didn't factor earlier, we could, it's just that if we don't factor, it's easier to find the horizontal asymptote. If it's factored, then we have to calculate the leading term from each numerator and denominator. So now let's factor f of x. So in the numerator, looks like we can factor x squared minus x minus 2. So that's x. We need 2 numbers multiply, give me -2. When we add, we get -1. So -2 plus 1. And then the denominator looks like that's x squared minus 2 squared. That's a difference of squares. So we get x plus 2, x minus 2. So it's completely factored. And now we're going to simplify, but we have to make note of what we simplified. So it looks like we get x minus 2 is a factor here. It's another factor in the denominator. So we can actually cross those 2 out. Give me 1. So note x minus 2 was canceled. You don't have to write this down, but I'm going to write it here because we need this information later on. So x minus 2 is canceled. So what we end up with is x plus 1, x plus 2. And now after we simplify, right, everything, we can set the denominator equals 0. So that's a step 3. So we're going to set x plus 2 equals 0, x equals -2. So this value is vertical asymptote. So that's how we find the vertical asymptote. Now, this is for graphing problem, which I'm going to graph later. So if I find a vertical asymptote, I have to decide, for graphing purpose, I have to decide whether the graph is going to be, remember earlier I talked about the graph could be either divergent, near there's a vertical asymptote, or convergent, right? So that's what I have to decide, which we're looking at the power, the exponent of the factors in the denominator. So here we're looking at the factor x plus 2. And what is the exponent of this? Well, it's just 1, right? Because x plus 2 has the exponent 1. So the graph is going to be divergent at this vertical asymptote. At this vertical asymptote. Because x plus 2 has a exponent of 1, has a power of 1. If x plus 2 has a power of 2, that's going to be convergent. All right, any questions about what I did finding the vertical asymptote and the horizontal asymptote? Now, let me give you a formal term that used a lot in calculus. You're going to learn this, see this very soon in 425. So a vertical asymptote on the graph is called a infinite discontinuity. It's just because the y goes to infinity or negative infinity. So we call this discontinuity infinite. That's just a term. Now there's another term called removable discontinuity. So that will be a hole on the graph. So a hole on the function on the graph is a removable discontinuity. Not every graph has a removable discontinuity, some do. Now, how do we find it? So to find a removable discontinuity, what we do is we look for the common factors in both numerator and denominator of f of x before we simplify. So look for common factor in numerator and denominator before factoring. Sorry, before simplifying. We already factored before simplifying. So that's how we're going to find the removable discontinuity or a hole in the graph. Now, if you remember earlier, I said, when we simplify, we cancel x minus 2, but we had to make a note of that, right? So this x minus 2 is where the removable discontinuity is going to be, which is x equals 2. So since x minus 2 is a common factor in numerator and the denominator, so x equals 2, so we don't take negative 2, we take the opposite number, x equals 2 is where the removable discontinuity is. So that's why we have to pay attention to what we cancel from the numerator and denominator, because that's actually part of the graph. If we cancel it, ignore it, then we kind of, change the graph a little bit. All right, so using this example, we found the vertical asymptote, horizontal asymptote, and then we found out the removable discontinuity or the hole in the graph. All right, so what's next? The next is horizontal. No, we did that. The next is the X-intercept and the Y-intercept. So find Y-intercept. Well, how do we find a Y-intercept for rational functions? It's just like any function, right? If you remember for lines, quadratics, if we want to find a Y-intercept, we make x equals 0. So we're going to set x equals 0. So go back to the function. I know it has been a while. Let's see. So here it doesn't matter. We can just use the simplified one. We don't even need to. So let's see. So in the simplified version, I just want to point out that even for the horizontal asymptote, we can use the simplified version, but just note that whatever you simplify, that will give us a removable discontinuity. So you can factor first and then try to find the horizontal asymptote. Just be careful there with the leading terms. So that's going to be, what did I have? I have f of x equals x plus 1 divided by x plus 2. So to find a y-intercept, we're going to make x equals 0. So f of 0 is going to be 1 over 2. So this is the y-intercept. And to find x-intercept, and just like before, we're going to set y equals 0. So if I set y equals 0, I get 0 equals x plus 1 divided by x plus 2. And I'm going to multiply by x plus 2 on both sides. So I get 0 times x plus 2, that's nothing. So I still have 0 equals x plus 1. The denominator just got dropped because it's multiplied by 0. So that's actually give us another shortcut. So sometimes people think, okay, instead of setting y equals 0, perhaps we can just set the numerator equals 0. So set the numerator equals 0 to find the x-intercept. Because the denominator doesn't matter what it is, I can multiply it by 0 on the left side and it doesn't matter at all. So that's another way to remember. For finding the vertical asymptote, you set the denominator equals 0. Find the x-intercept, you set the numerator equals 0. But if you don't want to remember this, just say, okay, I'm going to set y equals 0. Doesn't change anything. So if I solve for x, I get x equals -1. And so here we have to pay attention to multiplicity. So pay attention to multiplicity of x-intercepts, because that's going to tell us how the graph is going to behave at each x-intercept. So here we have x plus 1 to the first power, right? That's in the numerator, x plus 1 to the first power. So since x plus 1 has the exponent of 1, so x equals -1 has multiplicity of 1. All right. So I think we have done enough work for this problem, and then we can try to graph it now. So that's all we need. We need a vertical asymptote, horizontal asymptote, or any removable discontinuity, x-intercept, y-intercept, and that's pretty much it. So let's put them together. So graph it. So the first thing is I'm going to label all the intercepts. So I know that x-intercept is at -1. And it's going to be multiplicity of 1. So it's going to be straight cross. It could be like this. It could also be like this. I don't know, one of those two. Right. So I'm going to just draw a vertical line for now with a straight cross. And I have a y-intercept, which is at 1/2. So this is a y-intercept 1/2. I'm not even paying attention to the scales because that's not very important here. And what else? X-intercept, y-intercept. And remember at x equals 2 is the removable discontinuity. So let's just label it for now, but not do anything. So somewhere there's a removable discontinuity. So removable at x equals 2. And vertical asymptote is going to be at -2, and it's going to be divergent at -2. So x equals -2. That's a vertical asymptote. So I'm going to draw a vertical dotted line, and it's going to be divergent. Okay, here's a question. Coming in and okay, no problem. So if you missed part of the class, don't worry, the recording will be available. And the notes will be available. Try to find some time to catch up later. Good. All right. So that's a vertical asymptote. We found out that it's divergent because of the power of x plus 2, which is 1. And now we have one more thing, which is a horizontal asymptote, which is y equals 1. So that's going to be a horizontal dotted line at 1. Some people just draw the dotted line at the end. Some people draw it all across. It doesn't matter. Just keep in mind that horizontal asymptote. So this is a vertical asymptote. This is a horizontal asymptote. It just means that when x is really big, the graph is going to approach this dotted line. So I'm going to draw an arrow on both ends, but not in the middle. It could be above the dotted line or below or directly on it. I don't care. Right? So now we just have to piece together this function. Okay, so how do we piece this together? Well, you can either begin with the left or right. It doesn't matter. So let's see, we begin with the arrow on the left. So if I take the tail of this arrow on the left, and I could go down if I want, but there's no x-intercept to cross, right? So I cannot touch the x-axis. So, and I cannot just cross the vertical asymptote because that's also not allowed. So if I go down a little bit, then eventually I have to go up because I cannot, this is the x-axis and the vertical asymptote sort of create this like a blocking corner here. It cannot cross. So it can go down, but then I have to go up. Normally what we do, we just write kind of like going up, make it simple because we don't know exactly how it behaves. Right. So that's that part. And then remember it's divergent. So if left side of this vertical line goes up, the right side must go down because they're not going to go up together. They have to be in the opposite direction. And now we have this arrow on the right side of this vertical asymptote. We can take the tail and go up as we go right. And eventually it has to cross this x-intercept because it must be part of the graph. So it's going to cross this x-intercept at -1 directly, like a straight line. And it cannot just go up forever, right? Because eventually it has to touch the y-intercept. So it's going to come down here, touches it. And then how does it go after this? Well, eventually there's no x-intercept here. There's no vertical asymptote. They're just going to continue and then sort of following the arrow on the right. I'm going to erase this. So that's how we quickly sketch this. And then remember there's one more thing, which is the removable discontinuity at x equals 2. So we just need to put a circle here. So this point is actually not on the graph. So I'm going to erase this point and then put a circle. So that's how we draw the removable discontinuity. It's just a hole on the graph. One point is missing. All right, any questions about graphing this? All right, if you don't have a question, so let me go through another graphing example, because if you haven't seen this before, it could be difficult. So in this next example I have, I'm just going to kind of go down the list and try to find all the terms that we needed. So we have f of x is already factored, so given. F of x is equal to x plus 1 squared, x minus 3, and then we have x plus 3 squared, x minus 2. So if we quickly look at this, nothing cancels, right? So that means the graph is not going to have any removable discontinuity. That's fine. So nothing cancels. That's okay. All right. So let's find the horizontal asymptote first. So we need the leading terms of the numerator and the denominator. So leading term of the numerator, so I have to take all the x's and all the exponents and the coefficients, multiply them together. So I get x from the first parentheses squared times x from the second parentheses. Then the denominator I have x from the first parentheses squared times x from the second parentheses. Okay, so it looks like it's going to be just 1 again. Note that it's not always going to be 1. So note, let's see if we try to find the leading terms. I have x squared, x over x cubed or something. That's going to be 1 over x squared. Then what we do is we're just going to find out what this is going to give us when x goes to infinity. X goes to infinity, we get 1 over infinity squared, which is 0. X goes to negative infinity, we get 1 over infinity again, which is 0. So the 0 there will be my horizontal asymptote. So if what I meant is that if the leading terms don't cancel out, give us a nice number, what we do is we're just going to plug in infinity for x, see what we end up with. But in this case, we get y equals 1, which is nice. It's my horizontal asymptote. And then I'm going to find the vertical asymptote. We're going to set the denominator equals 0. So if I set the denominator equals 0 here, so I get x plus 3 squared, x minus 2 equals 0. So I get two parts. One is x plus 3 squared equals 0. So I get x equals negative 3. And x minus 2 equals 0. I get x equals positive 2. But note the multiplicity of each one. X plus 3 squared, the square tell me we're going to have a multiplicity of 2. So that means it's going to be the graph is going to be convergent because of the power of 2 at this vertical asymptote. And the x minus 2 has a power of 1. So that's sorry, it should be here. The exponent should be 1. So the x equals 2 has a multiplicity of 1. The odd number is going to tell me that it's going to be divergent at this vertical asymptote. Okay. And like we said, we don't have any holes or removable discontinuity. So let's move on to x, y-intercepts. So to find a y-intercept, what we're going to do is we're going to take x equals 0, put in there. So we get f of 0. So set x equals 0. So we get f of 0 equals 0 plus 1 squared times 0 minus 3 divided by 0 plus 3 squared, 0 minus 2. And if we do that, we get 1 negative 3. So 1 times negative 3 minus 3. 3 squared is 9. And times negative 2. So it turns out we get positive 3 over 2 times 9 is 18, which is 1/6. To be honest, it really doesn't matter what we have because we can change the scale for the y-axis, right? So as long as we know whether it's a positive or negative, that's the more important thing. So it's a positive y-intercept. And then the next thing we're going to do is finding x-intercept. So either we set the y equals 0 or we set the numerator equals 0. As it give you the same. So it doesn't matter which one we set it equal to 0 because the denominator doesn't really matter at all here. So we get x plus 1 squared times x minus 3. So x plus 1 squared times x minus 3. Double check, that's right. So that's going to equal to 0. So we get x plus 1 squared equals 0. So that gives me x equals negative 1. Then I have x minus 3 equals 0. Give me x equals 3. Again, we have to note the multiplicity of each one. So because we have x plus 1 squared, so x equals 1 has a multiplicity of 2. And the x minus 3 has an exponent of 1. So that has x equals 3 has multiplicity of 1. Because that's going to decide how the graph is going to cross the x-axis at those intercepts. All right, with that said, now we can actually graph it because we get plenty of information. So when you sketch it, don't worry about the scales on the x-y axis because we don't need a lot of points, right? Just the intercepts. So I have x equals negative 1. So I'm going to call this negative 1 and it's 3. So 1, 2, 3, So at x equals -1, it has a multiplicity of 2. So that means the graph is either going to be from above, it's going to come to this point and bounce up, or it's going to come from below this point and then stay below. So one of those two shapes. We don't know which one it is, but just remember it's going to be a U-shaped here. And at x equals 3, it has a multiplicity of 1, so it's just going to be a straight cross, whether it's like this or like this, I don't know, but it's just a straight cross for now. Okay. So that's the x-intercept, and the y-intercept, like I said, is 1/6. I'm not going to say, okay, this is a 1/6, right? It doesn't have to be here. 1/6 is positive. I'm just going to say, okay, this is a 1/6, because I don't care about any other points on the y-axis. This is the only point I have, so I can say, okay, this much is 1/6. Like if you end up with a y-intercept, let's say it's like a ridiculously like difficult to calculate fraction. It might be like, you know, like, I don't know, 125 divided by 17 or something. Don't even bother to figure out how big that is. Just note that it's positive, right? And then you can just pick a point on the y-axis, say, this is my y-intercept, this is the scale. All right, let me keep going. So the next thing I have is vertical asymptotes. I have two. At -3 is convergent, +2 is divergent. So let me write down -3, -2, -3. So there's a one vertical asymptote at -3 that's going to be convergent. And what's the other one? What did I see? +2 is going to be divergent. So +2 is here. The graph is going to be divergent. And I'm just going to extend the x-axis a little bit longer. And I remember there's a horizontal asymptote, which is at 1. So I already picked 1/6 to be the y-intercept. I don't want to spend too much time fixing it. So I'm just going to say this is my horizontal asymptote at 1. So this is a horizontal asymptote, y equals 1. Which means the graph, the two ends of the graph is going to be at those, going to be parallel to this dotted line. It's going to approach it in the long run. Okay, so, well, let's graph it. It doesn't matter which side you begin with. You can begin with the left, all right. Last time I began from the left, so this time I can begin with the right to show you how it works. So if I begin with the right side, I'm going to take this arrow here, and I'm going to take the tail. So I'm just going to move left with the tail. So as I move left, I cannot draw like this because then I'm not going to touch the x-intercept. So I have to go through the x-intercept. So that means it's going to cross this x-axis like a straight line. And then it's not going to go back up because there's no point to cross. And there's a vertical asymptote. Remember, we cannot cross vertical asymptote. So what we do is just going to continue left, but then go downwards like that. So it's approaching that dotted line eventually. So it looks like this. And obviously the actual graph is a lot smoother, but its overall shape is the same. And it's divergent. So on the right side is going down. That means on the left side, it must going up. So there's an arrow going up here. And then again, I'm moving left. So don't worry about crossing the horizontal asymptote. As you can see, I'm crossing it. That's perfectly fine to cross horizontal asymptote because the middle part of the graph, horizontal asymptote means nothing. So as I move left, and eventually I'm getting close to this y-axis, so I must cross this y-intercept. And after I cross the y-intercept, I can go up if I want to, but at some point I have to go down to pass the x-intercept. So if you want, you can draw it like that, but that's not nice. So I just say going down and down to cross this x-intercept, but it's not going to cross it direct like to the other side because it's a U shape. So if it's coming down on the right, then they have to go back up because it's a U shaped. and it's just going to go back up. And you probably think, okay, can it come down to the x-axis again? You can make the graph go down a little bit, but there's no point to cross. You cannot cross below cross the x-axis. You cannot cross the vertical asymptote. So then you have to go up. Again, it's going to cross the horizontal asymptote one more time. Right? Okay. And what about the remaining part of the graph? It's convergent here. So that means the arrow on the right is going up. Then it must be going up on the left as well. Okay, so if it goes up on the left, what do we draw the tail? Does it go directly horizontally towards the horizontal asymptote? Sure, that's fine. And we don't know. You could also go down a little bit and then go back up and become flat. I don't know. You know, to be honest, here it doesn't matter. There's no right or wrong answer here. So that's a graph. Any questions about this graph? All right, I hope you have seen this before, or at least a little bit, because if you have not seen graphing rational functions in the past, definitely spend some time, practice a little bit more with it. All right, let me give you 1 minute to finish writing. I have 2 more examples. I don't think we're going to take half an hour, so there's a hope that we're going to finish a little bit early, so just be patient here. Let me bring the 2 examples done. It's at the top. So what I'm going to do next with you is we're going to, so let's cut this. And we're going to take 2 functions that we already know the graph of. So what we're going to do is we're going to find the function for each rational graph, each rational function that was graphed. You can consider this like a sort of a little bit easier approach because you already know what the graphs look like. You just have to extract the information from it. Oops. All right. My computer is acting a little bit funny when I try to resize this. There we go. Okay, here we go. All right, so before I move on to the next 2 examples, any questions about graphing? Again, horizontal asymptote, vertical asymptote, X-intercept, Y-intercept, removable discontinuity. Those are the 5 things that you need to pay attention to. And before I do that, you know what? This is a good point to practice domain and the interval notation. So let's write down the domain for this function and the range before we move on. So let's see, a side note, we can find the domain of this function. And as you can see, the domain really affected by the vertical asymptote, right? It divides the graph into multiple pieces. So even if we didn't have the graph, if we have the vertical asymptote and the removable discontinuity, we should be able to write down the domain, which is going from -infinity to -3, but that's not including -3 because it's a vertical asymptote. And the next interval we have is from -3 to 2, but we do not include either end. And the last interval we have is from 2 to infinity, but we do not including 2. So that's a domain. What about the range here? Well, the range, be careful, the range is not affected by horizontal asymptote. So horizontal asymptote has nothing to do with range. The range is difficult to find if you don't have a graph. So you do need a graph to find the range. It's just whatever the graph covers, right? So on the left side, we know that it's going from 1 all the way to infinity, and in the middle, it actually goes all the way to 0. On the right-hand part, all the y values from -infinity to 1 are covered. So it looks like all y values are covered. So from -infinity to infinity, there's no y value that was missing. So that's the range. Okay. Questions? All right. No questions. Let's go through this last two examples here. So the first one I have, so given this graph, find a rational function. So what we do is we're just going to look at it and decide what goes into the numerator, what goes into the denominator. So the rational function looks like f of x equals, there's always a, just like in the polynomial function, that's a constant we don't know, but we need to find it. So it's going to a times something, something, maybe has an exponent that's not 1, and it continues, right? So let's see what we know. The numerator is from the exponents. So it looks like we have the numerator coming from X-Intercept. Looks like we have X-Intercept at -2. And it looks like it's not a bounce off, like a U shape. It's not a chair shape. It's actually a straight cross right there. That's a straight line, straight cross. So that's going to be X minus -2. And that's going to be has an exponent 1. And it looks like another X-intercept we have is at 3. That's also going to be a straight cross. So X minus 3 to the power 1. And there's no other X-intercepts. Okay. And let's look at the denominator, which will be based on the vertical asymptotes. So we have 1 at X equals -2. So that's going to be X minus 1 at X equals -1. So that's going to be X minus -1. And looks like that's going to be a convergent vertical asymptote. So because they're both arrows going up. So that means it's going to have an exponent of 2, perhaps an exponent of 4, right? And then what do we have? We have another vertical asymptote at X equals 2. So X minus 2 in the denominator. And it's divergent here, so it's going to have an exponent of 1, maybe 3, but for now we just use the simple one. So that looks pretty good. We just need to figure out what A is. And remember the small points we can use, right? It looks like we have a Y-intercept at 3. So use Y-intercept, Y equals 0, 3 to find A. So if we take 0, 3, put in there, so I get 3 equals A times, you know what, I should do one more thing. Sorry about that. I should simplify the parentheses. So if I simplify this, I get A times X plus 2, X minus 3. Denominator is X plus 1 squared, X minus 2. So now I'm going to plug in the Y-intercept. So I get 3 equals A times 0 plus 2, 0 minus 3. Then I have 0 plus 1 squared, 0 minus 2. And if we be careful, we get 3 equals A times 2 times -3. That's a -6 in the numerator. 1 squared is 1, -2 in the denominator. So we get A times 3, so A equals 1. So I get f of X equals A plus 2, X plus 2, X minus 3, and then I have X plus 1 squared, X minus 2. And we should always double check the horizontal asymptote, see if it makes sense. So check horizontal asymptote. So if we take the leading term of the numerator, we get X times X, X squared. If we take the leading term of the denominator, I get X squared times X, which is X cubed, so we get 1 over X. Okay, let's see. If X goes to infinity, I get 1 over infinity should be 0, approaching 0, right? So we get Y equals 0. So as X goes to plus minus infinity, Y goes to 0. That's right. So we have a horizontal asymptote Y equals 0. All right, any questions about this process? So I find it easy in the sense that if you want to find the factors in the numerator, just looking for X-intercepts and how the graph cross those X-intercepts. If you want to look for the denominator factors, we just look for vertical asymptotes and consider the convergence and divergence at each vertical asymptote. And to find A, just use any point that's given that's not used yet, usually the Y-intercept. And horizontal asymptote, you probably don't need it until the very end to just check your work. All right, if you don't have any questions, I'll move on to the next one, but let me pause for a minute. Any questions about this example? All right, then I'm going to move on to the next example here. So this example, again, we're going to do the same thing. I'm going to write down the rational function is f of x equals some constant a times whole bunch of parentheses in the numerator and also in the denominator. It depends on how many we need. We can keep adding them. So what do we have? We're going to look for x-intercepts. Looks like we only have one x-intercept at 1. So that's also a straight cross. So that's going to be x minus 1 to the power of 1. Now here you have to be a little bit more careful because we also have a removable discontinuity at x equals -1. If you remember how we find the removable discontinuity is we're looking for common factors in numerator and denominator, right? So that's what we do. If we have a removable discontinuity at x equals -1, which means we're going to have a common factor x minus -1 in both numerator and the denominator. We don't want to cancel them. If we cancel them, we change the function. So that's a common factor. And there's no other x-intercepts. Well, let's look at the denominator. We have a one vertical asymptote at x equals 3. So that's going to be x minus 3 in the denominator. It's divergent, so the exponent is 1. Okay, that's pretty good. And there's no other vertical asymptote. Let's check, see if we get it right. Let's try to find A here. So it looks like we can use any other points that we know we haven't used yet. I guess we could just guess what the Y-intercept is. Or maybe we can find some other convenient points on the graph. Looks like that might be a good point to use, 4, 3. Or maybe this might be a good point, 2, -1 is also a good point. So there's quite a few points that we can use, but I prefer to use the Y-intercept. It looks like it's not very nice. You know what? Don't worry too much about it. So let's see the Y-intercept is 0, x equals 0, y equals 0.4 or something, or 3. 5, 4. Okay, so let's just see Y-intercept is at 0, 0.4. We can use it directly. So that's a 0.4 equals a times 0 minus 1, that's a -1. And then 0 minus a -1, that's a +1. And divide by -3, and there's +1. And then if we simplify and find a, so we get 0.4 equals a over 3, and a equals 1.2. So I get the function to be f of x equals 1.2 x minus 1, x minus a -1, x plus 1. And the denominator is going to be x minus 3, x plus 1 again. I know we can check the horizontal asymptote. So if it's right, I feel like I probably didn't get it quite right. Let's see. So the horizontal asymptote, if we did it right, it's going to be 1.2. The leading term of the numerator is 1.2 times x times x. The denominator is going to be x times x, so we get 1.2. Okay, I can live with it. Close enough. So it looks like that's a little bit. That's about 1, but if we get 1.2, it's close enough. Don't worry about the issue at the end with the horizontal asymptote not being 1. If this is like an actual problem, I probably label what the y-intercept is. That way we don't have to guess what the value is. All right, any questions on this example? Oh, anything with today's class? I know there's a lot of information going on. All right, on that note, I'm going to let you go, but before I let you go, one quick comment about the quiz. I have not graded yet, so don't panic because I'm probably going to grade it sometime this weekend. So it depends on whether I'm going to have time to do it. If you, let's just say, if you don't get the results before Monday's class, don't panic. It will be graded at some point. All right. All right, take care, everyone, and I'll see you Monday. Bye.
Thank you.
Take care.
Thank you.
Yep. Bye-bye. Bye.